Recording. Before we start class, I want to make sure that you all remembered this Wednesday, 4:30 to 6, is the Friends of Science and Medicine seminar. It's in Physics 101, which is the building right across here. I guess it's supposed to be a nice classroom. We will have food. But if you are coming, please RSVP so we make sure we have enough food. Have you gotten the announcement about that? The announcement was sent out through many different outlets, but there's an RSVP link you click on and it takes you to Handshake.
Did Judy send it?
I don't think Judy sent it, no. I think there was one sent through Johanna Lewis, probably, through like, what is it, Health Care Alliance, something, I don't know. 4:30 to 6, right before this class on Wednesday. That means my office hours will also only be from, let's say I'll do office hours 3 to 4, because I have to go meet the seminar speakers beforehand.
Where do you RSVP?
What?
Where do you RSVP?
In the email there's an RSVP. So if you, I think the CAL's website also has it on it. So if you Google Friends of Science and Medicine UALR, does it pull up with the CAL's website? And if it does, maybe I'll send an announcement out tonight with a link so you can RSVP that way. Alright? I think that's it for logistics. Our next exam is next Wednesday night. Remember, once again, this is midterm, so there's 4 exams total, 3 midterms, and the final exam. They're all weighted equally, and the next exam will mostly be on stoichiometry and stuff we're working on today, so balancing equations, mole to mass to mole, mass to mass conversions. So let's get right into it. Does that sound good? Today's class is going to be all about practicing of how to use all these conversion factors we've been working up to all semester. To start with, we're going to do the analogy one. I think in lab you might have done the sandwich analogy. So we're going to do a s'more analogy. Just to make sure we're culturally inclusive, a s'more is a dessert that is an American treat and delight. It has crackers on the top and the bottom, so 2 pieces of cracker. It has 1 marshmallow that's in the middle that's usually heated up. And then it has, I'm going to call it 4 squares of chocolate. You can kind of see little lines between. So there's 4 little squares here. They come from a chocolate bar that's larger that has many squares in it. So I'm just going to say the number of squares. Okay? So we see 2 s'mores here. And there's an equation for how you'd make one at the top based on the ratios that exist. You're going to see why we're doing this in a little bit. I want you to go ahead and try to figure out, with the amount that we have, what's the most number of s'mores we could possibly make with all those ingredients. And if you notice, it says, show your work using dimensional analysis. So if you figure out the answer to logic first, that's fine. Show how to back it up with dimensional analysis. And so in the email. Okay. Come on. So figure it out. So if you had this in front of you, you figure out how you can make one. Why can't you just make a book? You make more. Maybe doesn't have a worksheet, we have a worksheet. All right, we have 33 responses. Use the logic first, then back it up with dimensional analysis. Ever?
Never. And then make sure we work out.
Your anti-paperwork.
Okay. How did you do this? We're going to hear from every person who wants to talk one time in class tonight. So if you're raising your hand, just know that that's going to be your one time tonight. We're going to try to get lots of different people to share their voices tonight. So who would like to share their thoughts on our first problem? How did you figure this out? Let's do the logic part first maybe, and then we'll talk about the dimensional analysis approach. John Paul?
Because there's 10 crackers, and you know it's 2 for s'more.
Speak up a little bit so people in the back can hear you.
It's 10 crackers and there's 2 for s'more versus the 6 marshmallows and 1 for s'more. And you got 64 chocolate squares and 4 for s'more.
So you said divided by 2 equals 5, divided by 1 equals 6, and then what about the chocolate squares? Did you figure that out? How many? Did anyone figure out how many s'mores we can make if we used all the chocolate squares? 16. So divided by 4, because we have 4 squares for every s'more. Is this an approach that most of you used? Well, so what if we'd had 4 marshmallows?
I would have cut it in half.
That's not how it works. We don't call it a s'more in my house unless you got a full marshmallow. It's really important, right? So this process that most of you just did off the top of your head is exactly what we call limiting reagent. It's a technical term that in chemistry scares a lot of people, but it is how much can we make based on what we run out of first. It seems pretty straightforward, right? We run out of crackers first, so we can't make more than 5 s'mores.
What was the name of the term?
Limiting reagent. So why is it called reagent? What is a reagent in chemistry? We have reagents and products, reactants and products. Where are the reagents? So the ones that we start with are all reactants or reagents. So limiting, which one limits us out of the ones on the left side of the equation? So that term allows us to figure out what our theoretical yield is. Can someone put that term theoretical yield in normal people speak? Our theoretical yield here is 5 s'mores. What does that mean? What's that, Tony?
What's expected to come out like what you would think should happen?
I might tweak that a little bit in the absolute best case scenario. What might happen? Right? So you said what might happen, but in chemistry we know that things go awry a lot, and so we don't always expect the best case scenario to happen. So it's what is the max? What is the best we can possibly do? Does that make sense? So it's not, I don't want to say that we're always expecting the best case. So this is the best case scenario. And is it based on the one that we have the most of? What is it based on?
The one that's top priority. The cracker.
Based on the
Crackers
limiting.
not the top priority. What kind of household do you have at home?
I would argue that the chocolate.
The cracker hold it together.
I mean, to me, it's all about the marshmallow. It's the top priority.
It's the foundation.
I can burn my fingers for a good marshmallow. So regardless of personal preference, how can we be more specific? Best case scenario based off of what? Morgan?
It's the limiting one part of it.
Based on the limiting reactant or the one that runs out first. So if we figure out which one runs out first, we can figure out what our best case scenario is that we could ever possibly achieve. We're never going to get to 16 s'mores with this. Why? We're going to run out of crackers, and we're going to run out of marshmallows. So those two limit our production. Specifically, the one that limits it the most is the crackers. So let's put that in the terminology that we're using in chemistry. So just click in. Let's make sure this is kind of a check-in. What is the ingredient that is the most limiting? Or you can put in multiple numbers if you think there are multiple things.
So it's not like a nursing question, it's not like what's the most.
Select all.
Yeah, what's the most right? They're all right. but which-
Yeah, which one?
Oxygenation.
A couple more seconds. Okay, based off of the results that are coming in, a majority of the class is saying that crackers are the ones that limit us. That's because that's the one that we run out of first. So, another term in chemistry that we're really interested in is, what's excess? What are our excess reagents? Which ones do we have left afterwards, after we're done and we ran out? So go ahead and click in which numbers we're left with in excess. Okay, a couple more seconds. Closing out. So we have a mix of, we have a mix between, let me pull it up, 3 and 2 and 3. What do we think? So is this one the only one that we're left with afterwards? Chocolate squares. How many marshmallows are we left with after this is done? We have 1 marshmallow left over. So both of these are excess reagents. So excess is for anything that's left over. Let's say that we kind of work in a household that is not so adept at making s'mores. And we actually are only able to make 4 of them. What is our percent yield? Think first for 30 seconds. Answer this question on your own, and then check with the person next to you and see if you come up with the same answer. Think on your own first. Make sure you have an answer. I hear a lot of voices. Hopefully you came up with an answer first. All right, let's do a couple more seconds. Do another 15 seconds. We have 5 of us in here to help you tonight. So this first part is going to be a little quick, but then the rest of the class we're going to spend a lot of time working. Make sure that you call one of us over, please. All right, we're at 42 responses. All right, the majority of us have answered 80%. How do we find that? What are numbers that are reasonable for percent yield? How do we think about this? What's reasonable and how do we get an answer? Maybe you can do multiple parts because Donald wanted to answer and I don't want to limit him in his response. Okay, so we figured out that our actual, we only made 4. Our theoretical, we could have made 5 in the best case scenario with the one that runs out first. And then what did you say after that? Okay, so this is an equation. How do we know if that's a reasonable number? How do we know if we memorized an equation and we flipped it or did something stupid?
If you flipped it, then it would be over 100.
Okay, so let's get to what is a reasonable value. Is a reasonable yield over 100%? You've never gotten over 100% in your labs up to this point.
Yep.
I see a number of people nod their heads. I've been in your labs. I've seen a number of people getting over 100%. What does that mean? It means you did something wrong, either in your calculations or in your lab itself. Most of the time, you have to dry your product, and so if you don't fully dry it, you're left with water, and hence it's heavier than in theory it's supposed to be in best case scenario. That's one of the major causes of a wrong theoretical yield. So if this number ends up being plus water or plus something else, maybe you didn't separate the things like you're supposed to. Maybe you got some sand in there at the end in one of those labs where you're supposed to separate things. But overall, theoretical yield should never be greater than 100%, and it should never be less than what? We're just saying what range it can be. It can't be less than 0. If you get a negative number, no bueno. All right. So we're going to use some of these terms kind of throughout the night, but I wanted to start off with something that hopefully you can visualize. You can do the mental math on your own, and you're thinking about how many do I have. What if I gave you instead, we have a box of crackers that weighs 52 grams, and some chocolate that weighs 6 pounds. Could you use those types of numbers to answer the same question?
If we knew how many pounds of each made us more.
Say it again nice and loud.
If we knew how many pounds each thing made us more.
Okay, we could. What would the other way be? So instead of saying, well, how many pounds of chocolate, how many pounds of marshmallow, how many pounds of cracker goes into each s'more, what's another way we could answer this?
Break it out and weigh it.
So let's say that we have this is what you had starting. Talk to your neighbor and try to figure out how could you figure out how many s'mores you can make. That's not what I'm saying. Think about what you'd have to know. So what's the... First of all, with just the weight by itself, can we figure out how many s'mores we can make?
No.
But we have 42, 45, and 62. Can we just use those numbers and those coefficients?
No.
What do we still need? What is imperative in order to use those stoichiometric quantities with the weight? What type of conversion would we want? I don't think we're going to have a mole of s'mores. Let's not go there. That would be enough to feed the world, everyone since the inception of the world until the end of the world as humans are concerned. And then some.
Okay, since we know how many of each we have, can we say like for every 10 crackers it's 42 grams?
Okay. Yes-ish. Can we say it in a cleaner way? What's the key piece of information we need for each ingredient? Tara?
How many grams is in, is like one s'more?
So we need to be able to convert from how heavy to how many. Does that make sense? If you knew that every graham cracker was half a gram, we would know exactly how many graham crackers we had. If we knew that every marshmallow weighed 2 grams, that wouldn't work mathematically, but you catch my gist, right? Then we could figure out how many, and then if we knew how many, we could figure out which one runs out first. So we have to go from how heavy to how many. And that is exactly what we're doing in chemistry. That's where most people get stuck. So with that said, let's start in on it. So today, I want us to be able to go from how heavy the reactants are to how many products or how heavy the products are that we can make. And then in doing so, maybe we don't have exactly the number of each that we need, just like the s'mores example. Maybe we're going to run out of one first. So I want you to be able to determine which one we run out of first and how much you can make at most. All right. So let's go ahead and we're going to do this octane example. We didn't do this in the last class, did we? Octane? Okay. So the question is, how many grams of carbon dioxide are produced when we burn 3.5 moles of octane in open air? Try to start this on your own. Spend at least 30 seconds to a minute thinking about how we might set this up. And then go ahead and flag one of us down if you get stuck and the person next to you is stuck. Question number 5 in the worksheet.
She's confused.
This is what I got. So, because there's so many, and that's a little baby, that was a little baby too. Boom. Look at that. Because you can have as many options as you want. There. Alright, so here's that. Alright, so this is an 8 plus 2 is 16. So 16 is there. That gives us 32 each. And 18 oxygen. Which is 16 oxygen. That's what I did. I could have used it. It does make sense. Because that leaves you with a lot of
on this side, or like,
an odd number of oxygens, excuse me. And so, then you can't.
So it's 225.
Okay, first of all, if you have that.
can't. Why? We're on the homework.
It does on the homework, it's on here. Dr. Belford, Dr. Bailey was on these. At least in here. You can do this, yes. No. And it can become confusing later. Oh, this is not a whole. You have to do time to do by 2. So 2, 25, 16, 18. Here. 2, 25, 16. You don't have to use all about what is another gram tool? Because we said something, right? Well, it's actually the whole 2 grams. Oh, you know the number. You know the number of moles of octane that's asking for the grams of CO2. First, how did we get it? gravy too. What? Now I'm gonna go from bowls of carbon dioxide to grams of carbon
Oh, yeah, that's fine. Yeah,
Because if you make a mistake, there's the right symbol in there.
Oh, I see what you're saying now.
So let's bring this together and talk through the first couple of steps, and then make sure that I give you some more time to finish the problem. Can I get everyone together for just a minute? Jay, thank you. So when you see a problem like this, I kind of hinted at what the first step is by the way I wrote the problem, but what is the absolute first step? And we're going to go ahead and do, I think the second one's actually with the same problem, right?
Yeah, well.
So how many grams of water, should we do this as numeric so I can actually get a more reasonable response? How many grams of water are produced if you burn 75.3 grams of octane in the open? First, make a solution map. What is your starting quantity? What are you trying to get to? What steps might you have to do in the middle? And we're going to do 3 minutes from now. So when that clock reaches 3 minutes and 30 seconds, we're going to talk through this one. Because we have a number more I want to do, and we have 25 minutes class left.
feel like that.
So I may have went about this a long way, but it's the only way I can compute it in my head. Or is that right?
Water. Grams of water. Coefficient ratio.
I think we passed the 3-minute mark, 3.5-minute mark a while ago.
Yeah, that's fine. So, what's the numbers?
So let's walk through a solution map version first, and then we'll do numbers afterwards. Can I have a new volunteer to talk me through what the solution map would be? Shelby. So just focus on the units. So we'll start with, we have grams of octane. And then what do we need to get to? Hold up. Let's do the two bookends first. So we start with grams of octane, and we're trying to get to grams of H2O. And what intermediary steps do we need in order to get there? Okay, so we need to go from how heavy it is in grams of octane to how many in moles of octane. And then, can we go directly from moles of octane to grams of water? What are we missing in between?
How many molar water to octane?
Okay, so we need to find moles of water. So these are the 3 steps we need to do. Each arrow represents a step. What are we going to use to go from the weight of octane to the moles of octane? Just the conversion factor. So we need to use a molar mass to go from grams of octane to moles of octane. Sorry, someone yelled it out here as we were talking that. And then how do we go from the moles of octane to the moles of water? What ratio, Sarah? So it's a 2 to 18 ratio, molar ratio from the stoichiometric coefficients. And then the last one, how do we go from the moles of water to the grams of water? Molar mass of water. Okay, so let's go ahead and write it out. So we have 75.3 grams of octane. And then we use the molar mass. What is the molar mass of octane? That's how heavy 1 mole of octane is. I didn't verify that number, so if you're a little bit off, don't get stressed. And then what's our molar ratio that we use? And then we just need to say, we know how many moles of water we have if we stop now, but we can say, well, how heavy are they? So to do that, we use 1 mole. Wrong. 1 mole of water weighs 18.0. What's that? 0.02 grams. Okay? Shelby, what answer did you get for the number of grams of water?
106. Well, rounded it's 107 grams.
So I think it was 106.9 grams is what a lot of people had on the paper, or 8 or something like that. And why did you round it to 107 grams?
Because we started with 3 significant figures, so we need to end with 3 significant.
So one of the things that you miss out on if you just try to go right into calculating things and throwing numbers in is this time we didn't start with the number of moles, so we had to add an extra step compared to last time. However, sometimes when people start with the number of moles, they want to do this step. They want to use the molar mass, but you don't need to. So if you figure out what your steps are first, and then you put it into action, it's going to be a much cleaner process. All right, shall we do one that's flipped around a little bit? So let's go ahead and this question, I heard that some of the print-offs skip the back side of the sheet or something. So this may or may not be on your sheet, and I apologize if that's the case. It should be on the back of the first page of paper. So go ahead, it's a pretty short question. It should be on your screens right now. I want you to figure out what's the solution map for this. What steps do we need to do? And then go ahead and calculate it. We're going to do about... Is 3 minutes enough time?
No.
Okay, so 3.5 minutes. Go. You guys want a little cheat? There's a cheat that might be useful in class. Obviously, you can't do it on an exam. There's this thing called Google that helps you find the molar mass. If you're comfortable finding the molar mass on your own, that you know you can do it on an exam, just go ahead and Google it in class. That's practice you might not need to calculate the molar mass. So let's look at this. Let's talk steps. First step. First step. Don't panic. Breathe. And then balance. Okay? If you just went ahead and did a 1-to-1 stoichiometric ratio, you're going to be very unpleasantly surprised because this isn't going to make any sense. If we start with 8 sulfurs, we have to end with 8 sulfurs. So in order to find a balanced equation, we need 3 S8s. We need 8 chromium dichromium trisulfides, and we need how many chromium? Okay? Now we know what the appropriate stoichiometric ratio is. So what's our solution map? What units are we starting with? Moving to, Tay, you want to go ahead?
We're starting with grams of dichromium trisulfide, and we're going to grams of carbon.
Okay. And then can we go directly from grams to grams?
No.
So what do you have to do first?
The mole of dichromium trisulfide,
And then?
and then to the mole of chromium.
And then last the grams. So we can use molar mass on the two ends to go from how heavy to how many, or how many to how heavy. And then the intermediary step is a ratio, using the balance equation. Okay? Do we need another minute to work through this on your own? Raise your hand if you'd like a little bit more time to work this one. All right, let's do 1 minute just to set it up. I'm going to try to squeeze one more problem in here, though, so we're going to do this quick. Work on the setup. Don't worry as much about the calculation right now if you haven't gotten there yet. All right, let's talk through this. Hopefully you've had a chance to write down the process. So I'm gonna look at Carmen's paper here for the sake of time. 10.0 grams of CR2S3. We can convert using the molar mass. That 1 mole of CR2S3 weighs 200.19. Is that what we have? Grams of CR2S3.
Where are you at? Yeah, 0.19.
And then for every 8 moles of CR2S3, we need 16 moles of CR. And then we can find out how heavy that is, because 1 mole of CR weighs 51.9961 grams. What value did you find? 5.9 grams of CR. How does that number look? 5.19 grams of chromium solid. Is that the right ballpark?
Yep.
Okay. So depending on what these values were that you plugged in, this value, and if your periodic table was the accurate one or slightly less accurate, you get slightly different values. How do we feel about this? So I highly, highly, highly encourage you when you're practicing to do these solution maps, to say what steps do I need to go through. And your workshop this week will be practice on that. So for our last problem of the class, I'd like to do this one, the first question here. I don't know why both of them showed up. So we're answering the first question here. We have a reaction between hydrogen and oxygen gas to create water. And it's balanced for us. We start with 2 grams of each. Which, if either, is our limiting reagent? Think about how you might answer this question. How many of them do you need? That's not how many each one is. It's like saying we need 2 graham crackers to make us more. We don't say how many 2 graham crackers are. We say every graham cracker is this heavy. And we need that's the molar ratio. The molar ratio already counts.
I mean, it makes sense, but just not.
Just some practice, I think, and seeing that that already is in play. On which? Yeah, I think it was at 5.19 grams. I think it was. I think. If you have something different, we can talk through it. All right, we have 39 responses. A number of people. Our majority answer is B. Why might our majority answer be B? And how might we calculate that? Did anyone have a rational reason for doing that? Or did just kind of oxygen look great? Maybe like a group of people, oxygen, oxygen, oxygen. Yeah. How do we answer this? Lena? Are you raising your hand?
No.
Donald?
I can answer which one's going to be used up first.
Which one is going to be used up first? So we have the mass is the same of both, and I wouldn't feel comfortable answering this question until I knew how many of each I had. So can you tell me how many hydrogen molecules we have? Can we calculate that? Yeah. So if we know we have 2.00 grams of hydrogen gas, we know that 1 mole of H2 weighs 2.016 grams. So how many moles of H2 gas do we have? Right about 1 mole, right? All right, what happens if we do the same thing for oxygen gas? 2.00 grams of O2. And we know that every 1 mole of O2 weighs 32, about 0.00 grams. So how many moles of O2 do we have? 2 over 32. What is that as a numeric value? 0.0625 moles of O2. Which one of those do you think we'll run out of first? For every 2 hydrogens, we need 1 oxygen. So if we are just looking at the hydrogen gas, how many moles of oxygen gas do we need to use this up, to use up both equally? We have to have twice as much hydrogen as oxygen. So we need to have 0.5 moles of O2. If we had 0.5 moles of O2, then it's twice as much of the H2 as it is the O2. Do we have more or less than 0.5 moles? We have a lot less. So that's one way to do it. The other way to do it is to say, okay, if I have this many moles of my reactant, I could have instead said, I know that if I have 1 mole of O2, I can make 2 moles of H2O. And I could say, how much water can I make from this 2 grams? I could have done the same thing here, right? See where I'm going with this? There's about 6 different ways to answer this question. What we're going to find is that all of them are going to say that we're going to run out of O2 first. Because our yield of water is going to be less if we look at it this way. We also don't have that 2-to-1 ratio we need, so we're going to run out of O2. So I'd advise to do the math and work through this. On an exam problem like this, I would probably give something similar to this, and I'd say, which one do we run out of first? And then maybe how much can we make? What's the amount we can make? So I'd advise just figuring out how much of we can make from each of the reactants, whichever one gives us least, right? We can only make 5 s'mores because we ran out once we made 5 s'mores.
Is it gonna be on the blackboard?
What's that?
Is it gonna be on the blackboard?
I will post the worksheet on Blackboard. There's a lot of other problems you can work through there. On Wednesday's class, we're going to do a little bit more on this, and then we're going to work on that ionic equations and solubility that you've done a while ago. We're going to get some practice on that.